All right, here's solutions for quiz 2 from Math 252. In this first problem, actually in all these problems, we're evaluating integrals, but this first one, unfortunately, we're doing it without the evaluation theorem. So back before you learned that we could figure this out if we just knew the antiderivative of the integrand here and then evaluated at 3 and subtracted what it's equal to evaluated at 1. Back before you learned that, you could still solve this problem. Just wasn't any fun, or I don't know, I guess it depends on your definition of fun. The way you did it is you express this area as a Riemann sum. So think about this as a whole bunch of rectangles. And so how many rectangles do you have? Well, I don't know. I'm going to call it n rectangles. Okay. And I want the area underneath this curve, so the sum of the area of all n of these rectangles. So what I'm going to do is I'm going to add up a whole lot of rectangles, all the rectangles from 1 all the way up to n being this unknown, but the number of rectangles that I'm going to have. And then the way I figure out the area of each individual rectangle, well, the area of a rectangle is kind of the length of the base times the height. So the length of the base, I'm going to use delta x to represent, and then the length of the height, I'm going to use f of xi. So f of x kind of gives me the height at some point x, but the problem is this thing's going to change. So I'm going to have a point that I'll call x1, my first x value, my first right endpoint, and then x2 and x3, I'm going to have to add those all up. So this is what I'm going to try to figure out. This will give me Rn, and then I'll later take the limit as n approaches infinity of this thing. So what you need to know is that delta x, the length of each of these rectangles, is the entire length we're looking at, so 3 minus 1, aka 2, divided by how many rectangles I have, which I have n here. So delta x in this case would be 2 over n. And then xi, well, the way you can think about xi is first figure out where you start. I start at 1 here. So in the first term, I'll have 1 plus 1 of these delta x things. In the second term, I'll have 1 plus 2 of these delta x things. In the third term, I'll have 1 plus 3 of these delta x things, and so on. So I can express this as 1 plus I times delta x. And delta x is 2 over n. So maybe I'll say 1 plus I times 2 over n. In other words, 1 plus 2i over n. In other words, n plus 2i all divided by n. I think as we saw in class that algebraically it ends up helping to put it into this form, get a common denominator, and add them all together. So okay, let's plug in the pieces here. I have the sum from I equals 1 all the way up to n of delta x, which we said was 2 over n, times f of xi. Well, here's xi right here, and f of x is given to me up here. So f of xi would be kind of this function with this thing put in place of all of the x's. So I got 3 times this thing, n plus 2i divided by n. That's the 3x part. And then from that I want to subtract x squared. And again, x I'm going to write as n plus 2i over n. And then let's figure out some parentheses here. I want this 2 over n to get multiplied by that entire thing. So this right here is what I want to evaluate. This will give me Rn, and then I'll take the limit as n approaches infinity of that thing. Okay, what a mess. Well, we can make life a little bit easier by a couple of observations. First off, there's a 2 over n in every single term. So I can factor that 2 over n out in front of this thing. And then I have the sum from I equals 1 to n of, let's see, from this term, I would have, let's see, what's the easiest way to do that? Maybe I'll take the 3 and distribute it through. I don't know that that's super smart to do, but let's try it out. So I would have 3n plus 6i divided by n from this term if I took the 3 and distributed through the numerator. And then from that, I would want to subtract, and I guess my denominator would be n squared, and my numerator would be whatever n plus 2i squared is equal to, which is n squared plus 4ni, if you FOIL this thing out, plus 4i squared. So I get here. And then how am I going to deal with this thing? Well, I kind of like having a common denominator throughout this thing. So I'm going to multiply this guy by n over n, and that will give me a common denominator of n squared. I'll have an n squared here and an n squared here. And if I got an n squared here and here, I might as well factor that all out in front and call this 2 over n cubed times the sum from I equals 1 to n of, let's see what I would have left. If I multiply by n over n here, I would have 3n squared plus 6ni minus all of this stuff. So minus n squared minus 4ni minus 4i squared. All right. So copying down this 2 over n cubed thing, let's see what I have here. I got 3n squared minus an n squared. So I suppose that I would have a 2n squared. I got 6 of these ni things minus 4 of these ni things. So I suppose I have 2 of these ni things. And then I have the 4i squared. And I have some information. I know about the sum from I equals 1 to n of I. And I know about the sum from I equals 1 to n of I squared. So I have a lot of information here that I'll be able to use pretty quickly. The way to think about this, or there's lots of different ways you can think about this, but one way you can think about this is let's leave the 2 over n cubed alone a little bit longer. And I got the sum. Well, maybe I'll wait to do that. The sum from I equals 1 to n of this term. So I got a 2n squared in the first version of these when I equals 1, and then a 2n squared in the second one when I equals 2, and a 2n squared in the third one when I equals 3, all the way until the nth one. So I have a 2n squared n times. I'm adding up n of these 2n squared things. So what I have is whatever n times 2n squared is equal to. I have n of these things that I'm adding up. So I have 2n cubed, but I'll write that in the next step. And then from this term, I got a 2n in every single one of these. So there's one here, and then there's another one, and then another one, and another one, and all that changes, the i's go from 1 to 2 to 3, all the way up to n. So I have a 2n in each one. I could factor out that 2n, and then what I would have would be an I in each one. I would have the sum from I equals 1 to n of I. But the sum from I equals 1 to n of I is written up here, is n times n plus 1 divided by 2. So this 2ni, I can factor out the 2n, and then I just have the sum of I, which is equal to this. Similarly, here I could subtract or factor out a 4, and then I would have the sum from I equals 1 to n of I squared, which I have written up here, is n times n plus 1 times 2n plus 1, all divided by 6. And so things are getting better, still kind of a mess. I guess I should close a parentheses here. But the big advantage is I've gotten rid of this sum. Right? I've managed to express this thing without this sum. So I'll be able to do some algebra and figure out what this thing is equal to. I guess here I have 3n squared. And if I wanted to multiply through, well, let's do that in the next step. So I got 2 over n cubed times. And then here I have 2n cubed. I think I said this was 3n squared. It certainly is not. N times 2n squared is 2n cubed. If I didn't say that, sorry. Then here, if I took the n and distributed it through the n plus 1, I'd have n squared plus n in the numerator here. And if I multiplied that by 2n, or how about just I multiply that by n? I cancel out this 2 and this 2. So this guy and this guy goes away. And then I got n squared times n plus 1. So what I would end up with would be n cubed plus n squared, coming from this term here. And then from this term here, it doesn't cancel out quite as nicely, so maybe I'll leave parentheses. I have this minus 2/3, and then if I FOIL this all out, n times 2n gives me 2n squared, but I have to multiply by this n, which gives me 2n cubed. N times 1 gives me an n, but 2n times 1 gives me 2 more n, so I have a total of 3 n's, and when I multiply by this n, I get 3n squared. And then 1 times 1 gives me 1, I multiply by this n, I got an n. What I'm saying is this is what I got now. Okay, so I have 2n cubed minus 2/3 of 2n cubed. Well, 2/3 of 2n cubed is 4/3 n cubed. So I have 2n cubed minus 4/3 n cubed. I have 6/3 of n cubed minus 4/3 of n cubed. What I'm left with is, let's do this in the last step, I guess. 2/3 n cubed, because this is 6/3 and this is getting rid of 4/3. Oh, and then I got another n cubed right here that I missed. Okay, so that becomes 5/3 n cubed. So 3n cubed, which is the same as 9/3, minus 4/3 leaves me with 5/3. So I've taken care of this guy, and that guy. What about my n squareds? Well, I have 1n squared here, but I have to get rid of 3n squared. So I have negative 2n squared. And then I have to, no, wait, I screwed that up. Shoot. I have 1n squared, and I have to get rid of 2n squared, because 2/3 of 3 is 2. So 1 minus 2 is negative 1. Wouldn't have changed my answer, but it would make my solutions look pretty stupid. There should be minus n squared here. And then with the n's, I just have minus 2/3 n. So finally, if I take this n, 2 over n cubed, and distribute it through, I get 10/3 n cubed over n cubed minus 2 divided by n, because I got an n squared on the top and an n cubed on the bottom, so that cancels with 2 of these, minus 4/3 with an n squared down on the bottom. And again, I got 1 n up top and 3 down on the bottom, so this is what I end up with here. So this is what our n would be equal to. And the integral from 1 to 3 of this function, which was 3x minus x squared dx, is equal to the limit as n approaches infinity of Rn, this thing right here. Well, as n goes to infinity, this goes to 0 and this goes to 0, so I would just have 10/3 left over. If you feel like checking your answer, you can pretty quickly. Let's see, check. Using the evaluation theorem, the antiderivative here would be 3/2 x squared. And the antiderivative here would be 1/3 x cubed. So that means that this integral is equal to this thing evaluated at these endpoints. So I go plugging in a 3 here. 3 squared is 9. 9 times 3/2 is 27/2. If I go plugging in a 3 here, I get 27 divided by 3 is 9. So minus 9, which I'm going to write as 18/2. So I got a common denominator right off the bat. And then from that, I'm going to subtract. Plugging in 1, I will get a 3/2 over here and a minus 1/3 over here. So I'd end up with 9/2 on this side. And on this side, 3/2 minus 1/3. Let's see, this is 9/6. And this is 2/6. So I'll get 7/6. If I want this to have a denominator of 6, I would have to call this 27/6. And 27/6 minus 7/6 leaves me with 26, which is equal to 10/3, which sure enough is the same as this guy down here. You don't have to do this check. I just thought you might want to see it. All right, I spent a long time on that. Sorry, these videos are going to be a long one. Let's see if we can go through this. Evaluate the following integrals. Hint that can be done with the u substitution. So what u substitution you going to do? I think what I would do is let u equal x squared plus 1. And if you did that, then du would be equal to 2x dx. So therefore, half of du would be equal to x dx. I wanted x dx because that's kind of what I have up here. That allows me to rewrite this integral as, I don't even like writing this. Fine, the integral from x equals 1 to x equals 3, I'm keeping track of my endpoints, of 1 over u squared du with a 1/2 hanging around. The 1 over u squared came from this x squared plus 1, which is u, being squared in the denominator. And the x dx turned into half du, which leaves me here. And so, okay, I can figure that out. Bring the 1/2 out in front. I'm looking at the integral. I could probably just do this all in one step. This is u to the negative 2 power. So if I took the antiderivative, it would go to u to the negative 1 power, but I need a negative 1 coefficient out in front. And I want to evaluate that from, again, it's x equals 1 to x equals 3. And so, okay, let's get back to x's so we can evaluate that thing. X is equal to, well, u is equal to x squared plus 1. So this is negative 1 over x squared plus 1, because this is negative 1 times 1 over u. And so there's the 1 over u over there. And I want to evaluate this from x equals 1 to 3, but I don't even need to write x equals because I'm back in my x's here. So let's see, that's 1/2. Appears in both of the terms, so I'll factor that out. And then I got -1/10. You plug in a 3 here. 3 squared is 9, plus 1 more gives you 10. And then from that, I want to subtract -1 over, if you plug in a 1, 1 squared is 1, 2. So if I needed a common denominator here, I could say this is 5/10. So I'm subtracting -5/10. That's the same as adding 5/10. So I got 5/10 minus 1/10. I got 4/10. So I got 4/20, which is the same as 1/5. So I end up with that as my answer. Moving on. Another u substitution here. I think the trick you will want to do is let u equal the natural log of x, and then du would be equal to 1/x. So you can do this dx, and you can do this all in one step if you want, or you could break this up into 2 different integrals. You could factor out a 1/x. There's a lot of choices in how you do this. I think what I would probably do is say that this is equal to the integral of, let's factor out a 1/x, and then what I have left is the natural log of x plus 1 over the natural log of x dx. And then you're like, oh, 1/x dx, awesome, that's exactly du. It works out really nicely. U is the natural log of x, so I get the integral of u plus 1/u du. So figure out the antiderivative. You got 1/2 u squared from this term, and from this term you got the natural log of the absolute value of u. I don't want my answer to have u's in it. U is just some placeholder. It's really the natural log of x. So I'll go and replace those. I'll get 1/2 natural log of x squared, because my u is supposed to be squared there, plus the natural log of the absolute value of the natural log of x. And then if you remember, you should tack on a plus c there for this indefinite integral. Okay, moving on to the back page here. All right, problem 3a. I actually screwed this up the first time I did it. So these are the incorrect solutions that are here. This is all wrong. What I did wrong, I don't know what the hell I was thinking, but this is dv here. When you're using integration by parts, you can let u be the natural log of 2x, and then the remaining stuff is dv. So this x cubed should have been dv. So if this said a d here, then I would be trying to figure out what v is equal to. And this is right for v, but they're just kind of mislabeled here. And because they're mislabeled, I screwed it all up as I went through the problem, put the wrong pieces in the wrong part. Anyways, my point is that all of this is wrong. Which if I cared more, I'd erase it so it didn't look like I made a stupid mistake, but what are you going to do? I made a stupid mistake. So I'm going to redo this problem down here. So 3a asks you to find the integral from 1 to 3 of x cubed, natural log of 2x dx. And it says in 3a that integration by parts would work. And so the integration by parts formula, as I mentioned before, it tells you that the integral of u dv is equal to uv minus the integral of v du. So I go and look at this guy, and I kind of have some decisions to make. I want to choose something for u so that when I change this integral into this integral, this guy will be easier to take. And the trick for that one is if you let u be the natural log of 2x, then its derivative du will work out really nicely. The derivative of natural log of 2x is 1/2x times the derivative of 2x, which is just 2, using the chain rule. But that is just 1/x dx. And that'll be really handy to have this 1/x dx, because what you'll see, what ends up happening is dv is kind of what remains here. So I don't really have any choice. It's x cubed dx. And then I can solve for v by taking the antiderivative of this guy, which is the 1/4 x to the 4th power. And then if I just plug things into this formula, I can get, let's see, I'll solve for the indefinite integral first, so I don't have to worry about the boundaries there. So let's just figure out the integral of x cubed natural log of 2x dx. That would be equal to u times v, u being the natural log of 2x and v being 1/4 x to the 4th power. So 1/4 x to the 4th natural log of 2x. I don't know if you can hear my kid yelling in the background. Whatever, don't know why to tell you about that. U times v minus the integral of v du. So when I multiply the two of these guys together, I get 1/4 times x to the 4th times 1 over x. And you're like, whoa, doesn't that simplify really nicely? Yep, sure does. I could pull the 1/4, the constant out in front here, and then all I would have left would be x to the 4th times 1 over x, which is precisely x to the 3rd power. So now, maybe over here, I can take this antiderivative. I got 1/4 x to the 4th, natural log of 2x, minus quarter of, and then this antiderivative is 1/4 x to the 4th. And I think I forgot part of this. I think the problem actually has a +1 in it here. So really what I should do, let's fix this after the fact, is I have a +1 dx here. But then I can say that that's just the integral from 1 to 3 of x cubed natural log of 2x dx plus the integral from 1 to 3 of 1. Sure, you don't need to write that 1 dx. And so this one will be easy to figure out, and this one is kind of what I'm doing over here. So I'm solving this part of the integral, and actually I guess I'm done at this point. I figured it out as an indefinite integral. All right, so I have, this is my indefinite integral, which maybe I'll clean up a little bit. I can pull out the 1/4 x to the 4th, I guess. Does that make it easier? Maybe. No, I doubt anybody would do that. Well, maybe you would. Sure. 1/4 x to the 4th. If I factor that out of both terms, then what I have left here is the natural log of 2x. And then over here, I've pulled out 1/4 x to the 4th, so I would just have a minus 1/4 left over. So it would look like this. And so now that I have this piece and this piece up here, I can figure out my definite integral. So maybe I'll do this half over here. The integral from 1 to 3 of this part, x cubed natural log of 2x dx will be equal to this thing. So 1/4 x to the 4th times the natural log of 2x minus 1/4 evaluated from 1 to 3. So let's go plugging in the numbers here. If I plug into 3, I get 1/4 times 81. And so maybe 81 over 4. Let's save a line. Times the natural log of 6 minus 1/4. And then from that, I want to subtract what I get if I plug in a 1. If I plug in a 1, I get 1/4 times the natural log of 2 minus 1/4. Something like this. Do you want to clean this up? I don't know. Maybe you do. You could. Oh, you know what? I'm not even going to bother cleaning it up. Can we just call this good? No. Okay, I'll clean it up. I got 81 natural log of 6 over 4. And actually everything's over 4. Now, I'm not even going to clean it up. I don't feel like doing any more algebra. Maybe I'll say or ... If you feel like simplifying that thing, you can. But I'm going to call that good. But then that's not my final answer. I have to take that answer, and I have to take this part here. The integral from 1 to 3 of 1. Well, that's just x evaluated from 1 to 3, which is 3 minus 1, aka 2. So then that makes my answer is this plus that. Which I'm sure you could clean up and find some numerical answer if you felt like it, but I'm just going to go ahead and call that good. Because I am incredibly lazy. And hopefully you can follow all of that, and so I'll call this good. All right, and then the kind of last one, this guy here, I think we saw something similar to this in class. This is a tricky integration by parts one. What you're going to do is let u represent the cosine of the natural log of x. And then you're like, wait a minute, that's everything. What's going to be my dv? Well, I guess I would be forced to just let dv be equal to dx. Well, then what would happen? Du would be, I'd have to use the chain rule here, the derivative of cosine is negative sine. And then I'd leave the natural log of x alone, and then for the chain rule, multiply by the derivative of natural log of x, which is 1 over x. And the antiderivative here, if dv is equal to dx, then v is just equal to x. So I can use my integration by parts formula to say that this guy is equal to u cosine, maybe I'll even write it over here, the integral of cosine of natural log of x dx is equal to the cosine of natural log of x times v, which is x, minus the integral of v du. Well, if I multiplied these two guys together, the x and the 1 over x would cancel each other out. So I'd have minus the integral of negative sine, aka plus the integral of sine of natural log of x dx. And then I stare at this thing right here and I'm like, can I take that integral? Is that any easier? Well, yes and no. I mean, it's kind of the same, but we're going to see this trick where I end up getting something like this. What I'll do is those steps over again. Maybe I need to switch colors here. To figure out this integral, I'm going to let u equal the sine of the natural log of x. And then I'm going to let, or therefore, du is equal to the derivative of sine is cosine. So the derivative of sine of natural log of x would be cosine of natural log of x times 1 over x. And if this is u, then dv is forced to just be equal to dx, and v is again equal to x. So what I can now say is the integral of cosine of natural log of x dx is equal to, just copying everything down, the cosine of the natural log of x times x plus, and then I got to write what this integral is equal to. Well, I can figure out this integral using integration by parts. It's this u times this v. So, I don't know, sine of natural log of x times x minus the integral of v du. But if I multiply the two of these guys together, what would happen is this 1 over x and this x would cancel. And so I would get the cosine of the natural log of x dx. And you're like, you're going in circles, stop already. Well, what you notice here is that I have the same thing on this side of the equation as I have over here. So I could add this over to the other side of the equation and get two of these things that I'm looking for, the integral of cosine of natural log of x dx. This one and this one would be equal to, I'm going to write this a little prettier, x cosine of natural log of x. I think it's pretty. And then this guy, x sine of natural log of x, and I'm adding them, I guess. So if I divide by 2, I get my answer. The integral of the cosine of the natural log of x dx is equal to half of this thing. How about this? X over 2 times cosine of natural log of x plus sine of natural log of x. Factored out that x from each of these terms, and then the 1/2, put it down on the bottom there. So this right here would be my answer.